Hello and welcome to my channel. Today I would like to build the spherical parallel joint. I think this is a really cool mechanism and I really would like to build it and see how it works. And maybe like this I will find out if there is some applications to this mechanism or it's not really useful mechanism. But anyway, if you have an idea where I can use it, please write this in the comment. I prepared some 3D printed parts. I prepared the stepper motors. So let's get started. Now let's look at the CAD model which I made, and for the disclaimer, I'm not 100% sure at this point that it's going to work. We will see this when we will assemble it. So this is my design. I actually put here only one part and you need to multiply it by 3. So it should be like over here, but with only one it's easier to see. So the motor is going to be fixed over here and it's going to drive this link. This link is rigidly fixed to the red link. Red link is fixed to the yellow one with the bearings over here, and the yellow fixed to the output. This green is output with the bearing. There are several important points here. First of all, the green link is situated kind of on the outer sphere shell. The red one is in the inside sphere shell, and the yellow one even in the sphere shell which is inside of the red one, and the green one, the output, even in another. So each of these links, they move on the concentric sphere shells, so they always stays on these shells. And to be sure that it's going to be like this, all the joints, all the rotational joints, like with the bearings and also the motor shaft, they should point in the center of these spherical shells. Another important point, that over here there is a 90 degrees over here, as you can see, and this link, it goes 90 degrees like this from here to here. The green one with the red one at 90 degrees, and also the red one goes from here to here also at 90 degrees, and like this it comes back exactly at the point where another motor should be. And in order to do this surface should be perpendicular to this one and should be perpendicular to this one. So all the mounting surface of the motors, they should be perpendicular to each other. And that's why this angle over here, it's not 45 degrees. So this is not 45 degrees. I made this mistake in the beginning. I made it 45 degrees and it was not working in the CAD. So this one seems like it should work in the CAD, but we will see if it's going to work in the reality. So as you can see from mathematical geometrical point of view, this parallel spherical joint is quite complicated and sophisticated. And the best way to understand geometry, mathematics and other science is to use Brilliant, the sponsor of this video. Why the Brilliant.org is the most effective way to learn? Because first of all, it's interactive, so you learn by doing. And the second thing, they slice the big topics at the small understandable chunks. Like this, even if you have just a couple of minutes, you still can learn something in this couple of minutes. So it's suitable even for the busy people, for the people who don't have much free time. Also, Brilliant has the 1000 lessons, the new ones added on the monthly basis. So there are a lot of them and you can find almost whatever you want. And one particular topic which is super important for this video, for the spherical parallel joint, is geometry fundamentals, because you really need to understand all these sinus, cosinus, all these complicated links, how they connected, interconnected. And the Brilliant.org is really cool in this because they have like an interactive way of learning. So you can see everything, you can try, you can move, you can change, and this is really perfect. To try it for free for 30 days, visit brilliant.org/scientific or click on the link in the description to this video. The first 200 of you will get 20% off from the Brilliant's annual premium subscription. Personally, I use the Brilliant in order to learn the neural networks, in order to refresh my knowledge in mathematics, which I have not used extensively recently, and the third thing that I use it in order to train my brain. So for me, there is these 3 points, which I hope are going to make me a better person. Okay, let's get started with the build. There are not so many 3D printed parts. All of them are 3D printed in this orientation like you see them on the table. I would also need 3 stepper motors, the metal collars for this, for the shaft of the motors, and some bearings. This is 1521 4mm bearing. These 3 parts are going to be the base of our joint. And these parts are going to fix these 3 parts together. So you see this part is like this, and there is some grooves over here and here. It fixes inside the grooves. And now we have the ring. This is a stand for the stepper. So the stepper is going to be fixed like this inside. But before fixing the stepper inside, we need to fix this part to this ring on this side. And for this, there is 2 holes here, 2 holes here, and it goes like this, embedded nuts inside. The M4 nuts goes inside, and the 24mm long M4 screws goes here, here, and this one on top. We have 1, 2 more to go. Cool, the base is ready. And the idea is that the base can either stand on the table or can be fixed on the wall with these holes. So you can put a screw in this hole and fix it to the wall. Now I'm going to fix the stepper motors. I use these stepper motors with the dual shaft, and like this, maybe in the future I will put the encoder at the back of the motor. But for this video I think I will use it without encoder. We will see. If I will have the time, I will put the encoder. This is NEMA 17. I'm not sure that it's going to be powerful enough for this, but we will see. I hope that it will be powerful. If not, I also bought the NEMA 23, also with a dual shaft, but in this case I would need to reprint some of the parts. One motor is fixed. Cool! For the next step I have 3 links like this. Each of these links goes to the shaft of the stepper over here, and I need to push fit it inside. Also there is a flat surface over there for the flat surface of the stepper, and over here I will put the metal collar with a long screw. So here I'm going to replace this short screw with a long one, and this long screw is going to pass through this hole. Like this, the torque is going to be transferred through this screw. So I need this piece over here just to make everything a little bit more solid. So this metal collar goes inside over here. And now I need to replace the screw. I have installed the collars and the screws over here. The next step, these 3 links, they should be fixed over here like this. There is a 4 holes for the 4 screws, for the 4 M3 16mm long screws, and here there is a places for the embedded nuts. The embedded nuts are installed. And again repeat this 2 more times. Next I have these links, which needs to be connected over here at the end, but these links should have the bearings inside, like over here. So the bearing is just press fit inside. And now this bearings goes inside this small axis, and this small axis is going to be fixed over here from the inside. So probably it's better to show it over here. So like this one, and afterwards over here 3 screws, which are going to be screwed inside our embedded nuts over here. For this I would need 25mm long M3 screws. This piece is not actually symmetric. Over here there is no any step, and over here there is a small step. And so right now we should use this one with the step. So the axis goes inside, just like this. It seems like it works. Now we need to repeat this couple more times. Now this piece is going to be the end effector, and the bearings from this last link will go over here. And this is just an axis which is pressed fit inside, and afterwards we're going to put the screws here and here embedded nuts. Embedded nuts first, because otherwise it's going to be nightmare to install them. By the way, over here I have 9 holes where I can fix something. And there is places for the embedded nuts over here. So like this I can fix something from behind. Okay, let's try to install it. One is installed. Second one. Ooh. And already now I can see if it's going to work or not, but we will test it just in a moment. Let me put all the screws. Yeah, this is why I need to put all the screws. Okay, the main mechanical assembly is done. Now the question, is it going to work? I can already check it by moving the motors by hand. I have not tried yet, so I don't know if I messed up with the CAD or if it's going to work. I'm actually nervous. If I move these two, nothing happens. And if I move this third one, nothing happens. Yeah, I messed up. What I did wrong. So actually in the middle over here there is a singularity point where I can move all the axes and it just does not move at all. Yeah, I have messed up when I was assembling. This one should go here. Look, I messed up when I assembled. Not when I designed it, but when I assembled. Right now I can move the motors and it just stays in the middle, nothing happens. This link should go here. And basically it's like this should be. This one like this. Can we correct it without disassembling? This is a great question. Yeah. This is the right position. Over here, like this. Haha. This is the right position because in this position I can move it like this. I can move it like this. And I can even turn it if I would have the 3 arms. But if I let it go, it can go in this weird position where, like, whatever you move, it does not move. Interesting. Also, I don't need to put a lot of torque on the motors in order to move it. So it seems like NEMA 17 could work. The better way to show you how it works is actually not to move the motors, but to move the output. Like this, in the right position, I can move the output like this to just rotating it. I can move it like this. I can move it like this. I have connected all the motors to this beautiful controller. If you would like to know more about this controller, you can watch my video about cheap 3D printed 5 degrees of freedom robot arm. The controller is powered by 24 volts and the signal to the controller comes via USB. The wires over here is just like this. We can try to run it, but before there is a tiny problem that, as you can see over here, this part touches a little bit this one. Yeah, this should be solved, and actually I already 3D printed the new parts for this. These are the 3D printed parts in order to fix this problem. So basically this is a new link which will go over here, and like this it will increase the gap between this part and this one. For the moment I don't have the encoders on the motors, but there is a possibility to put these encoders over here on this shaft. And also this controller has the input for the encoder. But today I'm going to use it without encoders, and so I need to find out how to fix this piece. The problem is that if we don't fix it, it can fall over here, and like this is kind of singularity, because over here, whatever motor rotates, the output does not move. And this is the worst position which you can imagine for the initial position. In order to fix this issue, I have 3D printed these parts. And my idea is that this is kind of worst position to start, but one of the best position to start would be this one. This exact position which I draw in the cut. So these pieces we can put over here. 1, 2, and over here the third one. Yeah, this is really a good position to start, but here I have another problem. So in total output is held by the three long links, and the length of these links is like this one, plus this one, plus this one, so they're quite long. And because of this, if you apply just a little bit of the load on the output, everything is moves. And basically that's why I don't like this possibility. I would prefer to hold the motors instead of this. And that's why instead of these parts, I've made these ones. And the idea is that this part goes here, so it's going to hold the first link. So it's like this. So our 3 motors connected to the controller. This controller is powered by this power supply with the emergency stop button, and the USB will go to the Raspberry Pi, and the Raspberry Pi we're going to control with the PS4 joystick, and like this we're going to move this spherical parallel joint. For the moment I'm going to control it axis by axis because I looked for the inverse kinematics and it's quite complicated, so I think it's going to be entire video about inverse kinematics for this parallel spherical joint. The firmware on the controller and the program on the Raspberry Pi is more or less the same program which I used in my video about 5 degrees of freedom robot arm. So that's why I'm not going to explain in details these programs. Joystick is paired. The power to the controller. Now I need to connect the Teensy. Next, run the program on the Raspberry Pi. Now the motors are enabled, so theoretically I should be able to remove these supports. Okay, so it holds the position, and now let's try to move it. It's a little bit tricky to control it individually, motor by motor. I really like this project. I think I would like to continue with it. And one way to improve this design is to make these links a little bit more solid, maybe a little bit thicker, maybe replace the NEMA 17 motors with the NEMA 23 motors, or add an additional reduction stage here. We will see. I would like to keep this simple project. I don't want to make it expensive, complicated, etc., etc. Another thing which I would like really to do is inverse kinematics. I already looked at the internet and you can find equations for the inverse kinematics of this parallel spherical joint, but these equations are quite tricky and complicated. So I need some time to understand them and to implement them. But I really want to do this. But anyway, thank you for watching this video till the end. Huge thank you to people who support me via Patreon and via YouTube channel membership. Here are their names. Thank you guys and girls, you are the best. As usual, this design will be available for some of my patrons. Stay safe, good luck with your projects, and see you next time.